Concentration is the amount of substance per 1 liter of solvent. In chemistry, we often want to know the concentration of a substance at a certain time in the reaction. For example, this is very useful when you want to know the concentration of a certain species in a specific time.
The reaction order of a substance can only be determined by experiments. For example, the chemical below has undergone 3 trials which determine the concentration and initial rates of A. You would see that from trial 1 and 2, the concentration has doubled. The same goes for its initial rate. You'd also see that from trial 1 and 3, the concentration has tripled, as well as the rate. To get the reaction order, you must find the exponent of the concentration that would produce a certain number. For example, 2 must be raised by what number to produce a value of 2? Likewise, 3 must be raised by what power to produce the value of 3? The exponent of the concentration is equal to 1, and thus we call this a first-order reaction. In a different experiment, let's say we've obtained different values for the rates and concentrations of A in 3 trials. You'd see that from trial 1 and 2, the initial rate has quadrupled. You'd also see that from trial 1 and 3, the rate has been multiplied by 9. We must find the value of exponent x that would raise the value of 2 and produce an answer of 4. Using our knowledge in exponents, we know that x equals 2, and thus we call this a second-order reaction. Let's say we conduct a different experiment yet again, and we find that in every trial, the concentrations of A correlates to the same initial rate each time. So, what value of x would turn 2 into 1? The answer is 0. Let's define some more terminologies before proceeding to the equations. In a chemical equation, the small a, b, c, d, and e are the coefficients of the reactants and products. The rate law is basically an equation that links the reaction rate to the concentrations of the reactants. X, y, and z are the exponents which represent the order respective of each molecule. Take note that the exponents are not equivalent to the coefficients. K represents the rate constant with units 1 over m squared times seconds. The sum of all the order of the reactants is the overall reaction order. For the zero order, the unit of K is m over seconds. For the first order, the unit of K is 1 over s. For the second order, the unit of K is 1 over m times seconds. You might be asking how the units were derived. Let's give an example. The exponents of A and B are 2 and 1 respectively. We already know the units of K, and so let's multiply it to the units of A and B, and this is what we get. Cancel out m cubed and m squared and you get m over s, which makes its order 0 overall. Let us now proceed to the integrated rate equations. For finding the concentration of A in a specific time, we may use the following equations. You may pause the video if you want a copy. All of these equations are linear, meaning they form a slanted line when graphed. You would notice that these equations follow the line equation y equals mx plus b. The zero order is slanted to the right downwards, as well as the first order. The second is slanted to the right upwards. This is why K is positive, hence it shows a positive slope. Let's define the variables. A0 is the initial concentration. At is the concentration in any given time. K is the rate constant and T is the time. Let's have some examples. Given that H2SO4 has an initial concentration of 0.01 m and K is equal to 3 times 10 to the negative 4th power, what is the concentration of H2SO4 after 30 minutes? The solution. Let us first convert the time from minutes to seconds. In the given K, its unit is 1 over s. Basing from the table, 1 over s is a unit for a first-order reaction. You can look at the units of K to determine the order of reaction.
So, 1 over S is a first order with this equation. However, we need to isolate A, so we must raise the whole equation and make Euler's number the base. Let's change the unit of K and make it M over S. The unit now makes it a 0 order with this equation. You do not have to isolate A since it is already so. Let's change the unit of K and make it 1 over ms, which is a second order reaction with a fractional equation. All we have to do is to multiply the whole equation by A to isolate itself.
We can derive a formula called half-life from the integrated equation. Half-life is defined as the time for the concentration of the reactant to decrease by half. It uses symbol T subscript 1/2. Again, we have different formulas for the half-life equation of each order. Remember that small a is the coefficient of the reactant. The rate constant for the decomposition of cyclobutane at 500 degrees Celsius is 9.2 times 10 to the negative 3. How long will it take for 80% of a sample of C4H8 to decompose? K is given and its units show a first order reaction. What we're looking for is time. We only know the value of K. A0 and A are not given. But remember that 80% of the sample has decomposed, meaning 80% of the initial concentration is lost while 20% remains. The remaining concentration is the value of A. Let A0 be x and A be 0.2x. We can now plug in the values. Then we cancel x, and then we get an answer of 1.7 times 10 squared seconds.